Hi everyone, I am Sachin from AccelerateAI, and in this video I'm going to talk about linear regression in depth. Linear regression is a very widely used technique. So in this video I'll talk about the premise of linear regression and its history. Also, regression is not just one technique but a class of techniques. I'll talk a little bit about some of the different forms of regression. Then we'll go and understand what are the assumptions of simple linear regression, what does the model say about, and how do we come up with a solution. And then we'll look at the model output and how to interpret that output with the help of an example. Then we'll go and talk about multiple linear regression with multiple variables. The interpretation of the model output are slightly different here than simple linear regression, so we'll talk about that. And then I'll also cover how to handle categorical variables in multiple linear regression. In real life, when we gather data and try to do some kind of modeling, it can often show some problems. When we create a linear regression model, it may not satisfy all the solutions. So we'll look at some of those problems and also some ways to solve them. And then finally, I'll touch a little bit upon the model diagnostics. So let's get started. So linear regression, as I was saying, is a heavily used technique, but it's also heavily abused. One of the common mistakes many statisticians and data scientists make is to extrapolate the linear regression line into an area where we do not have any data and then try to use the linear regression equation to predict for those regions. So this is not really correct. Now, linear regression, as I was saying, is very important. Predictive analytics, it falls under the area of supervised learning, but it came from the from the field of statistics. Linear regression is a statistical relationship. It's not an exact relationship, and I'll explain in a minute what I mean by that. So the basic setting of regression is you have a dependent variable, or you can call it a response variable. It's to measure the outcome of a study. Sometimes it's also called the target variable, and most often it's represented by y. And then we have a bunch of independent variables or explanatory variables, from which we try to explain changes in the response variable. And these are represented by x's. In regression, what we try to do is we assume a linear relationship, an equation like this, where y is a function of all these different explanatory variables x, and which takes the form beta naught plus beta 1 times x plus epsilon. So let's look at the picture here. We have the explanatory variable on the x-axis and the response variable on the y-axis. We have all these points, data points which we collected are plotted in blue color on as a scatter plot. And then what we are trying to do is come up with a line which is often called the best fit line. If the equation of the line is given by y equal to beta naught plus beta 1x, then beta 1 is the slope of this line and beta naught is the intercept. Now we can see that the points do not all lie on the line, red line. And that is why this error term epsilon is here. This is the error term, or also called the residual term, which is added in order to make this equation correct. So our primary interest here is to find the population parameters beta naught and beta 1, which are from the best fit line into that data. However, we do not have all the data. We only have a sample of data collected. So the parameters, the estimates that we get for beta naught and beta 1 are represented by beta naught hat and beta 1 hat. Also understand that regression model only establishes the existence of association between two variables. It does not say that y is caused by x. So it does not establish any kind of a causation. Usually we would want to understand causation, and that is how linear regression is used as well. But if we have to be very particular, causation has to be confirmed through controlled experiments. The very early forms of regression, one of the methods called method of least square was used in the early 19th century by mathematicians who were studying astronomical observations. Legendre and Gauss in the early 19th century used regression, one form of regression, to determine the orbits of bodies, planets, and asteroids around the Sun. Francis Galton was the first who applied regression to biology and to genomics. His famous study was named as rate of regression in hereditary stature. So he claimed that the height of children or next generation regresses towards the mean of that generation. And through data, what he showed is that children of taller parents are usually shorter than their parents, whereas children of shorter parents were usually taller than their parents. And that's why he said this is regressing towards the mean, from which the term regression came about. Modern regression analysis was further developed by R.A. Fisher in the early 20th century, where he came up with the idea of distribution of regression coefficient and goodness of fit. Now, today, regression is used in all functions of management area. It is used in finance, in capability asset pricing model, in predicting non-performing assets, probability of default and credit risk, and marketing to predict sales or market share, customer churn. It's heavily used in operations, HR, and many other fields. Regression, as I was saying, is not just one technique, but a class of techniques. The most common one is linear regression and logistic regression. Logistic regression is often used to classify something, but there are other forms of regression as well. There's polynomial regression, where the relationship between x and y may not be linear, but it could be in higher order polynomials. Stepwise regression is a form of linear regression, but here we try to come up with the most parsimonious regression model using multiple steps. Ridge, lasso, and elastic net, we again try to do that when we have a lot of variables or features. We try to reduce the total number of variables by penalizing the coefficients. In this video, we'll only talk about linear regression, but in subsequent videos, we are going to talk in depth about logistic regression and maybe also about ridge, lasso, and elastic net. Now, to understand, how linear regression works, we have a given population from which we will draw or gather some data, and that data essentially is drawing out from this larger population. So we will get some random sample. From that random sample, we try to build a linear regression model of this form, where beta naught hat and beta 1 hat are the regression parameters which are obtained from this random sample data. And then finally, we want to extrapolate that and say that these beta naught hat and beta 1 hat are unbiased estimates of the population betas. And we'll need to do some hypothesis test in order to prove that claim. While going into linear regression, let's first understand that there are certain very core assumptions of linear regression. And this is an area where I think a lot of data scientists do make mistakes sometimes. I have seen this in many of my interviews where people are not even familiar with the key assumptions of linear regression. So linear regression, as I said, we assume a relationship of the form y equal to beta naught hat plus beta 1 hat x plus some error term epsilon I. The first key assumption is that the parameters themselves are linear. Now, by the parameters, I do not mean x. X is the data point. What I mean by the parameters are beta naught and beta 1. Those are the parameters of the model. The regression model is linear in parameters. So that's the very first assumption. Often I have seen people say in interview that x has a linear relationship with y in linear regression. That may be true, but I can also use x square. I can transform x to x square and call that as a new variable, and I can then anyway call that a linear regression. What is important is that the parameters beta naught, beta 1, beta 2, beta 3, and so on always have to be linear. only in that case can we solve for these betas. The second assumption is that we know the accurate or exact value of x is. The explanatory variable x is assumed to be non-stochastic. The third one is again very important, and this is where I have seen a lot of people make mistakes. The error term or the residual term has to be normally distributed with a mean of 0 and some standard deviation. Now, this assumption, if this assumption is not valid, then the final model will be inaccurate, which would mean that our general form of relationship, there was certain problem with this, and we might need to make some kind of data transformation in order to then get the residual term to be normally distributed with a mean of 0. The fourth assumption is around the variance of the error term. So the error term has to have a constant variance. At any particular x, the variance has to be constant. And this has a name, it's called homoskedasticity. So essentially, homo means equal or same, and skedasticity is the variance of the error term. Also, in case of time series, mostly, we have to ensure that there is no autocorrelation existing between two error terms. Again, not between the data values themselves, but between two error terms. Also, an important assumption is around multicollinearity. This is the final assumption. If we have multiple explanatory variables, there should not be perfect multicollinearity between a set of those or a subset of those explanatory variables. Otherwise, our linear regression model will give us incorrect results. So these are the key assumptions. Very important to go through them and understand each of these assumptions, and then when we are building a model, we have to test for these assumptions as well. So now, we talked about linear regression. What we are trying to do is fit a line, and which we usually call the best fit line. So we have these data points given, and I'm trying to fit a line here. Now, there could be multiple lines which can pass through these data points, and there will be no line which will pass through all the data points. So how do I choose which line to take as my linear regression line? So very interesting. What is done in linear regression is, for each of these data points, a vertical line is drawn up to that best fit line. And the distance between this is essentially my error term, which is the actual observation minus the predicted value of that y at this particular x from this the red line. So this is my error term. What we want to do is minimize this term. In practice, what we do is there's a method to solve this. There are many different methods to estimate these parameters beta. One of the simplest methods is known as ordinary least squares method. In this, what we try to do is minimize the square of sum of these errors. The errors that we looked at, we try to minimize the sum of square of those errors. So sum of squared errors, which is for all the data points from I equal to 1 to n, we have epsilon square. If we expand this becomes yi, which is the actual value, minus my predicted value, which will be beta naught minus beta j times xij, j going from I to k. And we square this. The reason we want to square this is basically we want to look at the distance. We want to minimize the distance, and that is why we will square this term. If we do not square this term, and when we add this, it may come out to be 0 as well. Hence, we want to square and then get the best fit line. Now, how do we get the minimum of this? Calculus has taught us that to get the minima or add the minima, the differential of this particular function, this is also known as the cost function in machine learning terminology. So the derivative of this cost function with respect to its parameters have to be 0 at the maxima or the minima. So the parameters here for us are beta naught and beta j's. That is what we are trying to find out. So we'll differentiate the sum of squared error with respect to beta naught, which gives us minus 2 times sigma of I equal to 1 to n of this whole value. We assign it equal to 0. We also do a partial differential of the sum of squared error with respect to each of the beta j. If you have only one variable, there will be just one beta. If there are multiple variables, there will be multiple betas. And then we get this derivative of the squared error and assign that equal to 0 as well. Now for just one variable, if you want to solve this, we can very easily solve this for one variable, and that will give us beta 1 hat equal to this value, xi minus x bar into yi minus y bar, the product of these summed over all the data points divided by xi minus the average of xi squared summed over I equal to 1 to n. The top term is also called the covariance of x and y, and the bottom one is the variance of x. That's my beta 1. By substituting beta 1 into either one of these equations will give me beta naught hat equal to the mean of y minus beta 1 hat times mean of x for all the data points. So that's how I get my parameters for the sample from the sample data. Now let's look at how do we interpret this. So once we have built a model, there are softwares which will calculate the slope and the intercept for us, or the beta 0 and beta 1 and so on. The intercept beta naught is the mean value of the dependent variable y when the independent variable x equal to 0. And the slope beta 1, as we saw, it's the slope of that line. This is the change in the value of the dependent variable y for a unit change in the independent variable x. Now we have to, as I said, we have to remember that these values are for the sample data sets. Hence, we need to do a hypothesis test to then ascertain that these values are actually statistically significant. And the test that we perform here is called the t-test for significance. We assume that the null hypothesis is that beta is equal to 0, and then calculate the t-statistics for that and the p-value. If the p-value comes out to be less than our threshold value alpha, usually it is 0.05, then that implies that the coefficient or beta is different from 0, and hence there is a statistically significant association between that particular x and the target variable. Another way to look at the model and see how good the model is what is called the goodness of fit. It's the value is known as r squared. It's also called the coefficient of determination, and this is a measure of how close the data is fitted to the regression line. So the value of r squared is given by the explained variation from the linear regression model divided by the total variation in the data. So r square is given by 1 minus sum of squared of the residuals divided by sum of squared of the total. R squared is always between 0 and 0.1, but it's often multiplied by 100 to show it as a percentage, so it ranges between 0 and 100%. 0 indicates that the model explains none of the variability, which means none of the x variables have any impact on the y variable, and r equal to 100% indicates that the model explains all the variability in the response data. Though getting 100% will make me be a little wary and suspicious about how that data was collected. Generally in practice, r squared value of 0.75 to 0.8 or 75% to 85% is a good number. In general, higher the r squared, the better the model fits. But as I said earlier, it should not, if it's nearing 95% and above, then I'll suspect the data. So let's look at a simple example. We have a data of about 100 students uh, where their GPA, their SAT score in maths and verbal SAT score, as well as their final GPA when they graduated out of university, all these four variables are captured. Now the question posed is SAT a fair test? Which means, does SAT give me some kind of an indication of the final GPA of the person? So let's look at this. The way we'll analyze this is we'll write out the regression equations to calculate the university GPA from high school GPA, from math SAT score, and the verbal SAT score. So here's what I have done. This is something that I have done in Excel, but you could do it in R or Python as well. I got the equation y equal to 0.6748 times x plus 1.0968 for high school GPA versus university GPA, and an r squared of 0.6. On math SAT, I got an r squared of 0.43, and on verbal SAT, I got a r squared of 0.42. So note the coefficients and the constants here. Also the r squared values. And tell me, what do you think the r squared of high school GPA versus university GPA is higher than any of these? So do you think the SAT score is a better predictor of university GPA, or is it the high school GPA? And in that case, would SAT be a fair test? Let me know in the comment section, what do you think about these? Now I have a few quiz for you guys. So, the first question I have is, let's suppose we fitted a regression equation y equal to minus 4.3 minus 1.25 times x, and we obtain an r squared of 0.97. Which of the following statements is true? Our linear regression model will collectively predict y 97% of the time, or 97% of the variation in y can be explained by a linear relationship with x, or y and x have a strong positive correlation, or none of the above. Let me know in the comments which one do you think is the right answer. The second question is, the best simple linear regression model is the one for which the r squared coefficient is the highest, or the residual follows a normal distribution, the p-value corresponding to the t-test is less than the significance value, or the residuals follow normal distribution, the p-value corresponds to the t-test is less than the significance value alpha, and the residual are homoscedastic. Tell me your answers by commenting on the comment section. Now let's talk about multiple linear regression. So we'll extend that same logic of simple linear regression to multiple linear regression. Here we'll have several independent variables which will influence the response variable we are trying to study. When we have several independent variables, the regression equation is called multiple linear regression. So we'll have the equation now y hat as beta naught hat plus beta 1 hat times x1 I plus beta 2 hat times x2 I, and so on. I is the ith data point, and the first index 1, 2, 3, and so on refer to my different features, feature 1, feature 2, feature 3, and so on. The modeling steps here remain the same. We will hypothesize these features, which of the features we need to take in the linear regression model. Then we'll assume a linear relationship like this. And then we'll collect the data. From the data, we have to then estimate these model parameters, beta naught hat, beta 1 hat, beta 2 hat, and so on. Once we have done that, we'll also look at the residuals and check the distribution of the residual or the error term. And then we have to do model diagnostic. So we have here not just the t-test, but also the f-test, which looks at the overall statistical significance of the model. And instead of an r squared, we have an adjusted r squared that we'll look at in multiple linear regression. Once we are satisfied with some of those tests and the assumptions, then we can use that model for estimation purposes as well as for prediction. So here's an example or a picture for in the 2 dimension. We have x1 and x2 as 2 independent variables, and my y is the target or the response variable. Here, this equation gives me not a straight line, but a hyperplane in n-1 dimensions if I have n dimensions or n features to explain y. And as you can see, the value, the point here, this is the observed y. And if we take a straight line uh, projection of this on the hyperplane, it will lie somewhere here. This will be my predicted value. We could take a projection in any of the n minus 1 dimensions as well. Now, once we solve this, we will get all these betas. The interpretation of the coefficients of the beta is slightly different in multiple linear regression. So here, this is the partial regression coefficient, which essentially means that the beta is the partial derivative of y, or the rate of change in y, with a unit rate of change of x, given everything else is constant. And that's very important. And that's why it is the partial derivative. Now the relationship between r squared and all of these variables is, so if if I represent this by a Venn diagram, y1 is given by this upper circle, x1 is given by this particular circle here, and x2 is given by the yellow circle. And A, B, and C are the areas or the variance which is explained by x1 and x2. Then r squared essentially is the variance explained by x1, variance explained by x2, and there is some commonality between them. There might be some overlap between x1 and x2 as well. And the leftover is the variance that could not be explained by the linear regression model. So we talked about this model interpretation in multiple linear regression. We first have to, after we come up with the model, we have to test the overall significance. The first test that we do in multiple linear regression is the F test. This is a test of overall significance of the multiple linear regression. So our null hypothesis here is all of the betas are 0. So beta 1 equal to beta 2 equal to, and so on up to beta k, all of them are 0. And the alternative hypothesis is that not all beta values are 0. So maybe 1 or 2 or many of them are different from 0. Any of the modern softwares, including R and Python, will give us the output of the F test of multiple linear regression. Then we also have to test each of the individual parameters of beta, and for this we will conduct a t-test for each of the betas. And if the null hypothesis is rejected by a small p-value, then we will conclude that that variable xi adds significant information to the model given the presence of rest of the variables. So in the t-test, for each of the features, our null hypothesis is that that particular beta is 0, and the alternative hypothesis is that beta is different from 0. So the coefficients here, the betas of different independent variables, we usually cannot compare them if our unit of measurements are different. So let's say I have one unit in, one of them is in kilometers and the other one is in centimeters, then I cannot compare the two betas and say one of the variable has a higher impact than the other. In order to do that, in order to compare these betas, we have to standardize them. So there are what is called as standardized betas or beta weights. This is given by, the definition of this is the average increase in dependent variable when independent variable is increased by one standard deviation and the other independent variables are held constant. The standardized beta is given by the ratio of the standard deviation of x and y multiplied with that particular beta. The goodness of fit here, the r squared, if we keep on adding more and more explanatory variables, r squared will always tend to increase. So in order to correct for this, we use what is called as the adjusted r square. So we adjust the r squared by taking the degrees of freedom into account, or the number of explanatory variables. The adjusted r squared is given by 1 minus sum of square of error divided by n is the number of data points minus k is the number of features or explanatory variables minus 1 divided by sum of squared total divided by n minus 1. And the relationship between r and adjusted r square is given by this particular formula. I'm just showing the formula here for your reference, but it is not important for you to memorize any of these formulas. Most of these softwares will output R squared as well as adjusted R squared in the final output. Now, one interesting case comes up with is categorical variables. So in multiple linear regression, many of our predictive variables could be qualitative or categorical. As an example, education level could be represented as high school, graduate, postgraduate, or gender is female, males, and others, and so on. How do we use these categorical variables in linear regression? So for regression, these categorical variables are replaced with dummy variables or indicator variables, a method which is called one-hot encoding in machine learning parlance. So what we do here is, for a categorical variable with n levels, these are replaced by n minus 1 dummy variables. And for that particular category for which there is no dummy variable assigned, it is known as the base case. We cannot use n dummy variables because if we use n dummy variables, we'll have perfect multicollinearity among those variables, and then that will give us incorrect results in the final model. So as an example here for education level, let's say we have high school, graduate, and postgraduate. Let's keep the base case as high school, then we will create two variables as graduate and postgraduate. If both of them are 0, that is my base case scenario, which is high school. And then if the person is graduate, we'll put 1 for graduate and 0 for postgraduate. And if it's postgraduate, we'll put 0 for graduate and 1 for postgraduate. Right? So instead of one categorical variable education level, which has 3 values, we'll now have 2 variables, graduate and postgraduate. And each of them can take the value 0 or 1. And that is why it is also known as one-hot encoding. The coefficients attached to these dummy variables are called differential intercept coefficients. So they have a slightly different interpretation. They represent the change in the value of y from the base category, which is beta naught. The intercept beta naught is the mean value of the base category. So essentially, if the value, when we make graduate equal to 1, for that case is the beta here, beta 1, will show us the difference between the base case, which is high school, and when a person is graduate. Let's say we are trying to come up with a model to predict the income level of these people, or the income of these multiple people. The difference between what the average earning of a graduate and the average earning of a high school pass out will be given by this, the beta of that particular thing. And also important to note is if a dummy variable is not significant, it implies that it is not statistically different from the base category. So you can combine the category with base category and develop the model again using new set of dummy variables. Now, as I said, in real world, we may have the data may not always satisfy all of the assumptions of linear regression that we saw. One of the common issues is with multicollinearity. So if we have multiple variables and there is perfect collinearity among any of those, and if all of those variables are included in the model building, the coefficient estimates of the multiple regression may change erratically in response to small changes in the model or the data. So these are some of the signs of multicollinearity. One is that none of the t-statistics of the coefficient are statistically significant, but the f-test for the equation as a whole comes out to be significant. Another test of or sign of multicollinearity is that when you add an additional independent variable to the linear regression equation, it radically changes either the size or the sign of the coefficient from a positive to a negative or a negative to a positive associated with the other independent variables. So these two are telltale signs that there is some kind of multicollinearity among a subset of the variables. The other problem is with heteroscedasticity. So if we look at our residuals and if you see that there is this kind of a fanning out of the residual, then there is a problem in our model specification. When this kind of thing happens, then the Gauss-Markov theorem does not apply. The Gauss-Markov theorem says that the parameters or the estimates of beta obtained by ordinary least square equation are also the best linear unbiased estimators. However, in a case of heteroscedasticity, that will no longer be the case. So the betas that we get from our sample data may not truly represent the beta of the population. So heteroscedasticity causes the standard error of the coefficient to be biased, and therefore the inferences obtained for the regression, that is those t-tests, they are suspect. So the biased standard error lead to biased inferences. So the results of the hypothesis could possibly be wrong. We may be assuming that there is a statistically significant relationship between x5 and the y, whereas in reality it may not be the case. And finally, one important thing is the presence of outliers also impact the overall regression parameters, the betas. There are two types of outliers. One type of outlier is known as outliers with leverage. And these are the points which lie along the predicted regression line. So here, let's say the orange line is my regression line. If a point lies far away here, which is very different from the rest of the points, that will be a outlier with high leverage. The outlier with high leverage do not change the equation of the line itself, but what it does, it inflates the strength of the regression relationships. So it reduces the p-value, and then it also increases the r squared. The other type of outliers which are more dangerous are these kind of points which lie away from this regression line. So if we include or exclude these points, it will lead to a major change in the fitted regression function. As an example here, so if we include these 2 points, my regression line will shift to this blue dotted line. So this will impact, these points will impact all the statistics, including the p-value, the r squared, the betas or the coefficients, as well as the intercept. So what we talked about is, in order to use a model, a linear regression model, we have to do some kind of model diagnostics. First of all, we have to check the f-test to check the overall significance of the model. Then for each individual explanatory variable, we have to do the t-test. And then we also look at the r squared or the adjusted r squared to judge the overall fitness of the model. And if an r squared is only 0.05, then there is no point in using a model like that. In addition to these, there are a few other model diagnostics related to some of these problems that I talked about in the previous slides. I'll not go through this in this particular video, but if you want me to talk about some of these in a future video, do let me know in the comment section, and also subscribe to this particular channel so that I can keep bringing you some of these advanced topics on linear regression. In order to use a linear regression model, we also need to do a residual analysis, which can be done by either a PP plot or a QQ plot. We have to check for multicollinearity, which is usually done using VIF, variance inflation factor. Then for time series data, we also have to check for autocorrelation before developing a linear regression model. There's a test called Durbin-Watson test that is done to check autocorrelation. Also, we talked about outliers, so we have to do some diagnostics on the outlier points. We may not know which of those 5,000 data points are outliers. There are ways to do that. We can calculate the Cook's distance or look at the SDF fit or SDF beta in order to understand which of those points are outlier. Also, if we have a lot of variables, all the variables may not always be good in order to explain the final y variable. So often we do variable selection. It could be done by forward selection method or a backward elimination process or a stepwise method. And if you have been given variables and there's not a linear relationship between the x variable and the and the explanatory variable or the y variable, then we have to do variable transformation as well. And for that, we can follow what is called the Tukey and Mosteller's bulging rule to do those model transformation. So let me know if you want me to do another video on some of these model diagnostics. Now moving on, so here's what we talked about. These are our modeling steps. So we come up with a research hypothesis, essentially, which means that we say that these are the x variables which we feel are affecting my y variables. So we come up with that kind of a hypothesis. Then we gather data and then we will assess each of the variables separately. So we'll look at things like the central tendency and the frequency distribution. We'll try to study the data a little bit. And we'll also assess the relationship of each of the independent variables with our target variable. Is there a relationship? We can draw some scatter plots and look at that kind of a relationship. If we see that there is a linear relationship, then we proceed. But if there is not a linear relationship, then we have to go and transform those variables and then assess those transformed variable as well and see that there is a relationship. Once we establish that visually that there is some kind of a linear relationship between the variable and the target, we then take all the independent variables and we'll assess the relationship between those independent variables. We do not want any kind of multicollinearity in there. Once we do that, we'll build a model, we'll calculate the regression parameters, and then we'll check the residual plots using QQ or PP plot to look at any kind of pattern in the residual data. As we saw earlier, the residuals has to be normally distributed with a mean of 0. So if you see any kind of a pattern, which means the model specification was incorrect, and then we might have to again go back and transform the variables. If we do not see any kind of a pattern, then we will evaluate the model and each variable for significance using f-test and the t-test. And once we see that all of the variables are significant, if some of the variables are not significant, we'll drop those variables and then we'll rebuild the model again. And once we have done that, we'll interpret the model parameters, which is looking at those betas and saying, this particular x, unit change in this particular x leads to this much change in beta and so on. And then we can use that particular regression equation to predict for newer records. So in Python, we can do linear regression using two very powerful packages. One of them is called stats model. Stat models provide us many different types of regression. We talked about ordinary least squares, but it also gives us a lot of other things as well as good regression diagnostics, the residual plots, PP and QQ plots, and so on. We can also do many of the other types of regressions when some of the assumptions we talked about are not valid. The other package in Python which could be used for linear regression is the famous scikit-learn package for machine learning. Here again, there are many different types of regressions that could be done. Of course, ordinary least square, but we could also do lasso, elastic net, ridge, and so on. And there are all these metrics that are provided by scikit-learn as well to look at the various metrics or the output of the linear regression. So I hope this was helpful. Do let me know what you think about this topic, and if you want me to cover any of the other advanced topics or model diagnostics, as I said. Thank you so much for listening. And again, I am Sachin. And we, Kamal and I, are owners of AccelerateAI. We could be contacted on acceleratedatascience@gmail.com, or you can go to LinkedIn and look at us at AccelerateAI. Thank you so much.